Okay. Okay, so I will define the second part of the homework. I think the okay, so I would like you to prove the Jacobian for the three-dimensional solid element. The Okay, so the Cassini eta and the zeta coordinates, they are used for the mass element, and the XYZ coordinates, they are used for the real element. So we can define the vectors or the volumes in the mass element, and then we can calculate when we do the inverse geometric mapping, the corresponding volume in the real element. And after we calculate the volume in these two spaces, then we can calculate the ratio of these two volumes. And I mentioned that you can use the scalar triple product to calculate the two volumes. After you calculate the volume ratios, then you can calculate the determinant of the Jacobi matrix. Then you can prove these two, they are same, and then you can get the conclusions. The Jacobian represents the volume ratio of these two volumes. Okay, so that's the homework you need to derive, and also it is important. After these derivations, you can persuade yourself whenever you see the Jacobian, what's the physical meaning of this value. Okay, so that's the second part of the homework. And also for the load vector, and I will not mention all the details for the solid element problems, and you can follow the derivations used for the plane stress problems. So we can discuss the concentrated loads, and the concentrated loads could be applied to the nodal points, which is easier to calculate, and also not only it is easier to calculate, it is also can give you more accurate results. And but if it is required, you can also consider the concentrated load, which is applied inside an element. Okay, then we need to use the shape functions to calculate the corresponding point in this element. And again, probably you need to use the trial and error methods. You need to use the iterations to modify the trial values to find the corresponding Cassini eta and the zeta values for the load for the loading points. Okay. And also you can consider the distributed loads. The distributed loads, it could be applied along a boundary line of the real element. Also, it could be distributed over a surface for the real element. And if you like, also you can consider the distributed load which is applied on a curved line inside an element, or a surface. You can say it is a curved area inside an element. Also, you can consider such kind of the problems. And also, it is possible the distributed load which is applied over the entire volume in this element. Okay, there are all kinds of the applied loadings, and no matter which one you like to consider, we can always derive the corresponding methods. And after we calculate the work done by the applied loadings, usually we need to calculate the so-called the equivalent nodal load. The equivalent nodal loads, they are the loads applied directly on the related nodal points. And the basic concepts about deriving the equivalent nodal loads, they are based on the same work done by the really applied loadings and the equivalent nodal loads. Okay, so it is the same concept, but for the solid element, it is three-dimensional problems. So you need to consider one more dimensions, and you need to consider one more coordinates for the problems. Okay, and actually that's all the things I like to mention for the solid elements. And we still got some time, so I like to discuss the advantage and the disadvantage for the solid elements. And the advantage of the solid element, you can say it can be used for almost any problems. Okay. Okay, you can say the solid element can be applied almost to all the problems, since actually all the structures they must be the three-dimensional structures. No matter for example, if we consider a plate, although the thickness could be very, very small, but it cannot be zero. So you can say all the structures, they must be the three-dimensional structure. So if we use the solid element, you can say it doesn't have any kind of the simplified assumptions. So we don't need to consider the spatial characters for the structures. Just like if we consider it is a frame element, you can say it must be a slender element. If we say it is a plane stress problems, it must be a thin plate. And also we have some spatial consideration for the applied loading. For the plane stress problems, the applied load must be applied on the same plane of the structure. But if you use the solid element, there is no restriction for the shape of the structure. Also, it does not have the restriction for the direction of the applied loadings. you can consider all possible structures and all possible applied loadings. Okay, so especially for the mechanical engineering, for those commercial package derived from the finite element method, the most applications they are applied for the mechanical engineering more than the civil engineering. So especially for the mechanical engineering, they sometimes they always use the solid structures. They do not use very often for example, the plane straits, plate bending, such kind of the structural models. Most of the time, they just use the solid element and consider the structures, use the solid structural models. Okay, so that's the typical, but it is an advantage since it can be applied almost for all problems. And I think that's the most important thing for the solid structure. And what is the disadvantage? Okay, the first thing is the solid element use more nodal points and use more degrees of freedom. Okay, the simplest solid element, we need to use the 8 nodal points. But the simplest plane straits element, we need only 4 nodal points. And so the number of the nodal points, it is always greater than other structural models. And there are 3 degrees of freedom for each nodal point. So if we use the solid element, we need to use the U, I, V, I, and the W, I, the 3 nodal displacements along the X, Y, and the Z directions. So the minimum number of the degrees of freedom used for a solid element, it will be the 3 times 8. So it will be the 24 degrees of freedom. It is only for one element. If we remember, we need to define the elements to cover the entire structure. You cannot leave any part of the structure which is not covered by the elements. So the elements defined for the problems, sometimes you need to define a lot of elements, and also there are corresponding nodal displacements need to be assumed for the entire structure. So it is typical for a solid element, when we do the analysis, the total number of the degrees of freedom, it is very common to have the over millions of the degrees of freedom we need to consider. If we use the millions of the degrees of freedom, it means that we need to solve very large systems of the simultaneous equations. So since we need to have the same number of the equations with the same number of the unknowns, so if we for the entire problems, we need to use over millions of the nodal displacement. Also, for the stiffness matrix, it could be millions times millions. So it is a very, very large stiffness matrix. And also we need to follow the Gaussian elimination methods to solve the unknowns. So it takes a lot of integration times to finish these. So number of the degrees of freedom, the number of the nodal points, it also represents we need to take a lot of calculation time to finish the solution for the problems. Okay, so that's the first things. And also remember there is a requirement Okay, what is the aspect ratio? The aspect ratio means the dimensions of an element. Let me take the plane straits problems as an example. But for the solid structures, it is only one more dimensions we need to consider. If for plane straits problems, the dimensions for this rectangle, it is 4 and 1, and it is 1 and 1. Okay, so the aspect ratio for this element, which is equal to 4, since the length of the long edge divided by the length of the short edge, which is the 4 divided by 1. So the aspect ratio for this element is equal to 4. If we have the element which is 1 to 1, the aspect ratio is equal to 1. And what aspect ratio is best for the numerical accuracy? It is equal to 1. The reason is if you check the aspect ratio in the masked element, okay, in the masked element, it is the length, which is -1 to +1. So the length is equal to the 2. Also, the depth of the element, which is from the -1 to +1, the depth is also equal to the 2. So the aspect ratio for the masked element, which is equal to 1. So if you like to get more accurate results, the aspect ratio of the real element had better be close to the aspect ratio used for the masked element. Okay, in this case, you can get better accuracy. So it is also for the solid structures. In the masked element, the 3 edges, they are 2, 2, and 2. So the aspect ratio is always equal to 1. So it means when you define the elements, the 3 dimensions for the real element, it had better be in the similar dimensions. You don't need always equal to the same dimensions, but you had better be like 1.2 to 1 to the 0.9 or something like this one. So it is better. So it is better than if you define an element, you have one edge which is equal to the 10, the other one is equal to the 1. Then you cannot get very good results. Okay, so it is also a restriction for defining the mesh of the problems. So if you have a thin, so if the real structures, which is a thin plate, okay, for the thin plate, the thickness of the structures, which is relatively a small dimension compared to the dimensions on the plane. Okay, the real dimensions for the thickness, which is relatively small. If we consider the aspect ratio for the element, it means that on this plane, you need to also define the elements, which is you need to define a lot of elements on the plane. And since you don't like to get the aspect ratio, which is a lot different from the masked element. Okay, so based on the aspect ratio considerations, so it means that if you use the solid element, usually you need to define a lot of elements. The number of the elements required for the solid model, it is usually much greater than if you use the plane trace problems. Sometimes you can use much small numbers of the elements. Okay, so if you use the solid elements to solve the problems, you can expect you need to spend a lot of time, calculation time. Also, you need to you can expect you need to it is more complicated mesh problems, since you need to define a lot more elements compared to other structural models. Okay, I think I will end the course here, and the next lesson I will mention the plate bending elements. Okay.